Our next two presenters are Kirsten Singer and Dr. Sagar Srihari. I'll introduce them both, and then they can come up. Kirsten Singer is a forensic document examiner with the Department of Veterans Affairs, Office of Inspector General, Forensic Document Laboratory in Washington, D.C. She received her training in forensic document examination with the Virginia Division of Forensic Science, and then worked federally with the IRS and the U.S. Postal Inspection Service laboratories before transferring to VA/OIG. Ms. Singer has a bachelor's degree from the University of Virginia and a Master of Forensic Science from George Washington University. Kirsten and I were classmates at GW, and she was a really good student. She's been a document examiner for 27 years and is a member of the American Academy of Forensic Sciences, the American Society of Question Document Examiners, and is the current president of the American Board of Forensic Document Examiners. But Kirsten, I'm going to introduce Dr. Srihari before you start. So, Dr. Srihari, though we all heard him yesterday and today, but I don't think he was properly introduced today. So, Dr. Srihari is a computer scientist whose work is on automated systems for pattern recognition and machine learning. The principal impact of his work has been on statistical methods, on the analysis and recognition of handwriting, and in computational methods for forensic impression evidence. Dr. Srihari is currently a SUNY Distinguished Professor in the Department of Computer Science and Engineering at the University at Buffalo, the State University of New York, where he also holds adjunct professorships in the Department of Biostatistics and the Department of Electrical Engineering. And that's Dr. Srihari and Kirsten.
Thank you. Thank you, Jane. That's okay. You can find it.
You can do it yourself.
I'll see if I can find it. Okay. By the way, Jane wore a cute beret every winter at GW. Very distinctive. She's still very distinctive. Okay. This is a research that I had actually started about 5 years ago, but was derailed by some other QD issues, and was able to resume again last year with Tracy Moran initially, and then Dr. Srihari eventually. Counting characteristics is not a new thing for forensic document examination. Sampling of some of the research from QDAD shows that, for example, in 1963, Livingston looked at numerous handwriting characteristics in about 200 writers. In 1976, Mühlberger et al. Looked at a statistical examination of characteristics of the TH combination. In 1990, Huber looked at envelopes bearing writing of over 500 writers. In 1996, Rick Horton looked at various individual and class characteristics, including the Greek E and I dots, in a population of over 400 writers. And in 1998, Joel Zlotnick looked at the IT combination. In 2013, most recently, Brett Bishop looked at handwriting characteristics by people writing sections of the Bible. This is just a sampling. There are others. What I note is that, unfortunately, none of these focuses on the same thing. As examiners, we are looking at different characters and different characteristics, and nobody has taken a study and picked it up and continued, including me. Some of the current research you're already aware of, this one with Dr. Srihari and me, Lisa Hansen's, which I spoke of earlier, and Mr. Bastrick, who spoke at the beginning of the day today. And we're all looking at statistical frequency occurrence of handwriting characteristics. And thank you, NIJ. So the research that inspired my research was Mühlberger's 1976 published article in the Journal of Forensic Sciences, where he looked at the TH combination. He and others looked at approximately 6 characteristics, including the height relationship of the T to the H and the shape of the loop of the H. And they counted the occurrence of each of these characteristics. Because he'd already studied TH, I thought that's been done. My mistake. And I went on with the next most common trigram or 3-letter word in the English language, according to Wikipedia. A and D. Initially, Tracy Moran, another document examiner, and I developed tables and characteristics that we wanted to observe and note manually. And we made images of each of those characteristics so that we could say we were seeing the same thing. So, for example, we looked at the number of strokes for the formation of the A. Was it 1 continuous, 2, 3, uppercase, no fixed pattern? And you can see there are examples of each of those. Number 2, formation of the staff of the A. Is it tented, like the image A? Is it retraced, looped, no staff, no fixed pattern? Eventually, we came up with 9 characteristics for A and D. And we focused originally on handprinting because, as you've heard today, a lot of writers anymore say that they can't remember how to do cursive, or they don't do it comfortably. So you've seen this before. This is the truthing tool. Let me back up. The database that Tracy and I began to use was Dr. Srihari's over 1,500 writer database from his 2002 publication in JFS. I had contacted Dr. Srihari and asked for permission to use his database, which was extremely fortuitous, because he came back not long after giving me permission and said, hey, why don't we do this together, and why don't we work with automation of your observations? And I'm grateful to this day. He saved us from a lot of pain. So you've seen this before. This is the truthing tool. It extracts the words that you want to focus on and puts them all in one place for you to compare and view. And then you get a choice of cursive versus hand-printed. We expanded to cursive because with this automated tool, it was so much easier to expand. And his database contains both. So you select the button for cursive or handprint, and then you get the drop-down menus for that particular set of characters. As you select the character, it's saved in that text file as a number. So if it's tented, it's 0. If it's retraced, it's 1, etc. And you've seen this before. This is one of the text files of the writers. The writers by number, the page the writer has written by letter, and then the numbers designated for each of the characteristics that were observed. So in the end, God, I thought I got rid of that. I guess I didn't. In the end, you have a string of numbers for that combination of characteristics. And I went over this earlier too, so I won't repeat it. And this is where Dr. Srihari will step in and explain the significance of that string of numbers. And what we do hope to do is establish statistics that can maybe one day support our conclusions and also support one of our basic premises, which is that no two writers share the same combination of handwriting characteristics in a more objective way. So I'll hand it over to Dr. Srihari, and I'll finish up with a final slide. Next final slide.
Okay, a bit of repetition here from my talk as part of Lisa's, or yesterday, I think. So here we have this string here, and we can calculate what is the probability of that particular string based on the data set that we have. And there are two different ways of calculating this. One is using a so-called Bayesian network. And there is some confusion here. Whenever I say Bayesian network, people jump saying you're using a Bayesian technique. It's a bad nomenclature. The term Bayesian network was introduced by computer scientists. It didn't come from the statisticians. And they chose to use that word. Judea Pearl introduced that idea of Bayesian. It's got nothing to do with being Bayesian. It just has causality between variables. This causes this has an implication to another variable, and so on. So a Bayesian network simply is a network where you have nodes and edges. That's a graph, we call it. Nodes correspond to variables, and there are arrows pointing from one variable to the other, saying there is a causality between these variables. So Bayesian network has nothing to do with Bayesian analysis. And why is it called Bayesian? It's because there are conditional probabilities come into play, and that's what Bayes' rule is all about, using conditional probabilities. So there is one clarification here. So this is not Bayesian. These are all frequentist, actually. Bayesian network. And these are two different methods of computing. What's the probability of that sequence? Is the first one and the second one, the numbers are roughly the same. It says 1 in 10,000, right? That particular probability of that particular sequence is something like 1 in 10,000 if I'm interpreting e to the minus 005 correctly. Okay. All right. So the issue here is how do you calculate those probabilities? And I'll go over that again here. So the calculation of the probability of a given combination of characteristics is surprisingly very complicated. All right. How much data is needed? If we don't assume that the 9 characteristics are independent, if you assume all of them are independent, then the amount of data needed is not that high. We will need to determine, if we don't assume they are independent, we'll need to determine over 1 million probabilities just for this problem. You will need 1 million probabilities. We are talking about various combinations of these variables. And if you need 1 million probabilities, how much data do you need? 100 million to 1 billion samples. If you say I need at least 100 samples per bin and so on. And what about the time for computing all of these things, all exponential? So it becomes a surprisingly very complicated computer science problem. It goes away from the statistics domain into a computer science domain. How are you going to be able to compute all of this? Again, this is a repeat slide. It says, well, why don't we just assume independence of the variables? This slide was maybe it's too complicated to explain something extremely simple. It says if you have height and weight are dependent variables, if you assume independence, you get nonsensical results out of that. So you cannot always assume independence. And particularly with handwriting, when you have all these variables, like 9 variables that a document examiner defined, we don't know which of these are correlated and which of them are not correlated. We need to figure all this out by using some kind of computer program rather than simply say, oh, those are independent or dependent. So we really should not assume anything. So this leads into a very hot topic today in the field of machine learning. A big topic today is probabilistic graphical models. All right, you might have heard of this idea of these MOOCs, massive online open courses that are being offered on various topics. The very first course that was offered out of Stanford was on this topic of probabilistic graphical models. And it has become a revolution in this area called big data analysis. When you have many variables, the combinations are very complicated. How can you apply statistical methods to these kinds of data sets without making some arbitrary simplifications? So this whole thing is led by statistical machine learning and probabilistic graphical models. And what these models say is don't assume everything is independent, but there might be some independences that exist. If you don't assume some independences exist, the combinatorial possibilities are going to overwhelm you. So how do we discover what are dependent and what are not dependent? And there are 2 different approaches to it. One is what I mentioned already, Bayesian networks, which assume directed graphs, and the undirected one where you simply talk about these variables are related, but we don't know which causes which. They're just correlated. So those lead to what are called as Markov networks. So, and here is an example of for the cursive. For that handwriting set with those 9 variables, we end up with this particular graphical, this is a Bayesian network or a directed graphical model, and this is for handprint. But the number of parameters are not overwhelming. You need to estimate the values of 99 parameters. What are these parameters? These parameters are, the arrows say this depends on this, so you need a conditional probability. Given the value of this, what are the possible values for the other variable? You need these kinds of tables. Those are called as conditional probability tables or CPTs. So these pictures are accompanied by a bunch of tables. So if I give you some combination of these variables, I can always get the values from the CPTs and tell you what exactly that probability is. So learning these graphical models is not a simple thing. We just wrote a paper. These are taken from a paper that we'll be presenting. In August, there is a conference here in Washington called the International Conference on Document Analysis and Recognition. And we'll be presenting this particular paper that what is the algorithm that allowed you to come up with this kind of a graph? We just worked with the data and collected it. And this is a very current topic in machine learning. How do you learn these probabilistic graphical models without being overwhelmed by the so-called NP-hard problem? The computationally is not going to be feasible even with 9 variables and 4 or 5 possibilities. There are a few approximate algorithms. This was also learned by such an approximate algorithm. So this is what we are using here. So what we did, this is described in our paper that's in the IGDAR proceedings. We took our data set of handwritten ANDs, and every person's handwritten AND, for example, this one is characterized by a set of numbers. And given that number, and given the probabilistic graphical model, we can simply apply all the CPTs, or the conditional probability tables, and we can calculate numbers like this, 7.81 times 10 to the minus 10. I mean, it's an extremely small number, right? That's, 1 in a trillion, that kind of thing. We can calculate these kinds of probabilities. And so we can see which are the very common ways of writing an AND, which are very rare ways of writing an AND, in the sense if it's got a high probability, like 5.46 times 10 to the minus 3, that's 5 in 1,000. That's a very common way of that particular number sequence. 111022122 is very, very common, whereas some of the combinations such as 3132033301 is very rare. So we can say that's an unusual way of writing, or that's a common way of writing, exactly as described by document examiners, and using the statistical data that we have. So what we did also was we made a website where we put in all these samples of handwritten ANDs, and we simply list all their probabilities. We calculated in two different ways, one assuming they're all statistically independent, and then another one using this complicated model which says, no, let's look at all the dependencies to see whether we get exactly the same numbers or different numbers. Some of these numbers are all up there. Maybe many of them are independent if the numbers are very close. All right. So we are working with these things. My students are working on, this is a favorite topic of, actually I give it as a class project in my machine learning course, which is learn these probabilistic graphical models, given handwriting data, given that I have this data, I give it to them, and they have to construct these kinds of models. Some of these are here Markov networks where there are no arrows between variables. They are undirected graphical models. The learning of these things is much more complicated than learning the Bayesian networks where there is causality. All right. In summary of my part here, that the document examiners have defined a set of characteristics for the common word AND. We developed a truthing interface, and then the FDEs entered the data using the interface, and we, computer scientists, developed learning algorithms to create statistical models of this data, and we use these models to infer the probability of those characteristics. Okay, Christine.
And just to finish up, future research, we'd like to continue to mine the existing data for information and add individualizing characteristics. The 9 that we selected are arguably not at all individualizing. So it would be interesting to see what happens to the statistics, to the numbers, if it gets more unusual. I would like to continue to research the TH combination. Lisa Hansen is doing that with her kids, and I would like to pick up where Muehlberger left off and maybe expand a little bit and gather this kind of data. And also, I've gotten Marie Dorina's permission to have images of her study of the homogeneous writers and see how this system performs with writings that are much more similar to one another. So that is the end of our presentation. Any questions? Okay.
I noticed some of the illustrations that you had, Dr. Srihari's illustrations. There were some words that were sort of hybrids of cursive and handprint. I'm wondering how you made the determination of which group they went into, and with so many people now writing in forms that are essentially combinations of cursive and handprint, or script and handprint. How do you? Is there any
rule of thumb?
Well, rule of thumb, and do you compare them back and forth, the groups back and forth? For instance, in the words "and," I think it was the next one, the one that had the rare. No, it was one back. I'm sorry, the one that had some that were rare. And there you go. If you look at cursive rare, you see the A-N connected and the D always separate in the second from the bottom, and you find some that are very similar in the handprint. And that's what I was wondering about, whether there's any comparison of the two groups. and how you get them in their categories?
And actually I based distinctions of handprint and cursive on a study that Peter Teitel and I did a few years ago with Moshe Kam when he was asked to separate handprinting from cursive in his study so that he could develop error rates for handprinting. It's a lot of eyeballing. It's a judgment call. How many of the letters are connected, and of the ones that are not, does it appear to be a cursive character or more of a handprint? If there's uncertainty, we just discard the sample. We did not compare handprint to cursive in this study, but it was a judgment call. Sometimes it was a judgment call as far as whether it was a looped staff or whether it was a retrace. Yes?
You're going to further this study excuse me, with TH, which is not a word. So my question here is the and as a standalone word, or did you include and as part of a word also?
It's a standalone in this study.
Do you think it might be different? Do you have any opinions?
I really don't know. It's an interesting thought. Just to study an AN, for example, which is a very common bigram, it would be very interesting to see how those numbers would turn out. And that's something else we could maybe mine this data for, is to separate the letters and see which letters are maybe appearing a little more individual than others. Peter, of course, has a question. Oh, I'm sorry.
I realize it makes the statistics a little bit more complicated, but are you or is anybody using as a metric the degree to which something is cursive as opposed to printed? That is, not making it a 0-1 decision, but putting it on a real number scale, 0 to 1?
Dr. Srihari, do you have a comment?
We actually developed a computer program to take a small passage of handwriting to determine whether it's handprint or cursive on a scale. Okay, those of you who are familiar with the Cedar Fox system, it has that you open a document and it's got a moving scale there saying, is it more cursive or is it more hand printed? And how does it do it? We look at the discreteness of the handwriting there, in the sense if there are lots of different connected components, then that which means they're disconnected pieces, then it is more likely to be handprint. And if there are very, very connected types of things, then it is more likely to be cursive. So we have such a system, but and actually we evaluated it, and we do have a paper actually in one of the IGS meetings how well it performed on different data sets, and I can refer you to that one. So that's what we did, primarily the discreteness of the writing. But if you give a single word and ask whether it's cursive or handprint, it's going to have a hard time because it doesn't have enough information there. But when you have a whole passage of writing, it makes on a scale of 0 to 1, is it cursive or handprint? It gives you some number. 0.9 is it's cursive. 0.1 is it's handprint, like that.
And initially, Tracy Moran and I looked at the full bodies of writing in order to categorize them as handprint versus cursive versus we don't know. So in some of these instances, the and may look a little more handprint, but we had looked at the entire body of writing and were able to categorize it.
In the TH study, the Cedar Fox exemplar letter, which I, from the first day I saw it, started using in taking exemplars, one of the great things about it is that it has not just every letter of the alphabet, but it has letters in initial, medial, and terminal position. So with TH at the end of a word like with, or the beginning of a word like the, and in the middle of other, are you going to look at these perhaps to see what one can see?
Yeah, add it to the list. It's a good idea.
Hi, I'm just wondering, for the statisticians in the room, if this might be an issue that could be addressed using fuzzy logic, fuzzy set theory, perhaps?
Robert, you're not a statistician.
Yeah, we are taking a pure frequentist type of approach. What is the probability? Fuzzy people tend to be fuzzy. they say, well, somewhere here, in this, we're uncertain about it, so we are going to assign some value of our uncertainty to it. Yeah, our approach has been purely, calculate the probabilities to assign that probability. But sometimes it is not possible to get that probability, and you work with some values there, and then you build on top of it. So there's not a serious difference between fuzzy logic and probability theory, other than the fact that in probability theory we actually get it from data, and nothing is assigned kind of intuitively, right?
One more question?
Or a minor point, but you mentioned that Bayesian networks versus Markov involve causality, but is it not conditionality rather than causality? It is a subtle distinction, but I've always thought it the other way.
Okay, a good point. In Bayesian networks, you can simply talk about it as they're also referred to as causal networks. That does this variable cause the value of this variable cause the value of the other one to take some value? So it is terminology. Bayesian networks is a terminology, again, coming from computer science, and it just determines the causality to some extent. Causality is a very fundamental issue in science. Does this variable, like for example, taking vitamin D, does it decrease your getting arthritis? Right? Is there a causality of one and the other? In medical literature, there's a lot of this. There is correlation between the two, and then later on people found out that those who were taking vitamin D were also exercising. So the causality was between the exercise and arthritis as opposed to vitamin D and arthritis. So these are subtle issues, causality and correlation, that all the scientific disciplines face, and we also have similar issue here. But in Bayesian networks, we try to capture that causality by looking at the influence of other variables and so on. So it's a deeper issue, and there are algorithms now to address these. Causality is also a big topic in computer science today. There's actually a competition going on. Can your algorithm discover the causality between two variables? And and so they're trying to evaluate good algorithms. It's all completely statistically based, and so we are kind of delving into this area. It's a deep area.
Thank you.